Hello and good morning, everyone. Welcome to our tutorial session today. Our session title is Raising the Verification Bar, Cloud-Based Simulation Increases Verification Efficiency. My name is Ahmed Al-Zaftawi. I'm a Senior Partner Solution Architect with Amazon Web Services, or AWS for short. I focus on semiconductor and specifically EDA workflows and enabling partners and customers to run semiconductor and EDA workflows on AWS. In my session today, I'll be joined by Melvin Cardozo. He's a senior member of technical staff at Synopsys. So our agenda for today is to do a quick introduction, then we'll talk about verification infrastructure on AWS, followed by setting up simulation workflows on AWS and best practice for these. Then we'll have a Q&A session. And then after that, we'll have a demo of deploying solution on AWS. We call it scale-out computing on AWS that sets up an environment that's familiar for EDA workloads. And then we'll run Synopsys verification flow within that solution. And then after that, we'll have a wrap-up and Q&A again. So let me get started with the verification infrastructure on AWS. So Amazon is part of the semiconductor and electronics industry. We design our own silicon devices and we source components and parts from a global supply chain. And you can see the images and diagrams showing different use cases for where we use these semiconductor components. So we use them for our data center infrastructures. We also use them for our consumer devices like Echo devices that are shown at the lower right corner, or in robotics and AI that power our Amazon warehouses. And some of these semiconductor components are actually internally developed by Amazon engineers on AWS infrastructure. So as an example of Amazon Silicon are these three different categories of silicon chips. The first one is AWS Graviton, and then AWS Graviton2. Both of these are ARM-based, and we use them for our server infrastructure on AWS. We call these different types of servers, we call them EC2 instances. So these are powerful and efficient servers for modern applications that are ARM-based. And then in the middle is AWS Inferentia, which is a silicon chip that we use for machine learning hardware, specifically for inferencing, and it provides better cost optimization for inferencing at a large scale. And then finally, the semiconductor chips that are used by our own hypervisor, we call that AWS Nitro system. And there are three different semiconductor chips that are used to offload network, storage, and security so that the core server processor that you're using on the server is completely dedicated for the workload that is running. And all these semiconductor chips were 100% developed on the cloud from RTL all the way to Radius 2. So why, I guess an important question that we want to answer here is why AWS for our semiconductor and in general and specifically for our discussion today is easy workloads. So number one, it helps you to innovate faster. On Amazon network, we have our data centers physically located in what we call regions, and these and we have 24 geographic regions that that are in production use, and there are, at the time of the recording, there are 6 more regions that are pre-announced. And a region for us is essentially what we call a physical location, where we have multiple availability zones. And the availability zones are, and at this point, we have 77 availability zones. And these are distinct locations that are engineered to be insulated from failures in other availability zones within the region. So for example, the North Virginia region on the chart here has 6 availability zones. Oregon has 4 availability zones. Most other regions have 3. So these are important to make sure that you have essentially fault isolation. Again, each of our regions have at least 2 fiber network connectivity into our global network, and again, at least 2 power supply resources that, again, for redundancy. Okay, and as I mentioned, AWS offers a highly reliable, low latency, high throughput network that enables this connectivity around the globe with a fully redundant 100 gigabits per second network. The next important use case is it enables better collaboration. So either you are working with your EDA vendor or maybe consultants that are helping you with your project, for example, verification consultants that are relevant for the discussion here, or maybe any other type of consultants you might be working with. You can essentially deploy an environment in AWS. And that ties also to the third benefit about reducing risk, that where you would only upload the data that's needed for that specific workflow or for that specific consultant, rather than giving them access to your own complete environment. And then finally, it helps you to reduce cost of developing your silicon by, again, using the different purchase models, and I will touch a little bit upon the different purchase models for Amazon EC2 instances. So typically when we deploy an EDA stack on AWS, it's usually composed of multiple layers, as you can see on the diagram here. And that's where we would use a solution like the scale-out computing to help us deploying that EDA stack. So the solution would include, at the bottom, would include storage, either using Amazon EFS or FSx for Lustre, to act as our own high-performance either scratch file system or even high-performance high IOPS file system, where typically would run active simulations and active data sets on, or local disks that are attached to our EC2 instances. And then above that comes the servers, and typically for EDA workloads, we would use EC2 instances and auto-scaling so that we can scale up the cluster dynamically when we need additional resources, and then scale them down when we don't need them. And complementing these are our Amazon EC2 Spot instances, which are the lowest cost of EC2 instances that you can get. And again, I will touch upon the differences between the different EC2 purchase models later on. And then obviously on top of that, you would have infrastructure support for a license manager, a job scheduler, maybe a directory service, and then on top of that, remote desktops or login servers for users to access the cluster and be able to submit their jobs and so on. So the core component here that I wanted to focus on this slide is the compute side. And there are different instance families that are available on AWS. The most relevant ones for our discussion today would be, for example, the ARM-based instances that, or what we call the Graviton2, or powered by the Graviton2 processor that's developed by AWS. And these are available on 3 different instance families. We call these the M6G, the C6G, and the R6G. And the main difference between them is how much physical memory per core is available on the system. But all of them are based on 64-bit ARM Neoverse N1 that is designed by AWS. It's based on a 7-nanometer silicon. Instances within the family come in different what we call instance types. These allow you to select how many cores you want and how much memory you want in the instance. So on the largest size of the instances, you can get up to 64 physical cores and up to 512 gigabytes of DDR4 memory. Also, the C6G and has a newer advanced networking. The C6GN actually you can get up to 100 gigabits per second. But on all of them, the M6G, the C6G, and the R6G, you can get up to 25 gigabits per second of network throughput. And typically these families offer 40% price performance advantage over the corresponding x86 gen family, for example, the M5 or the C5 or the R5. Okay, and relevant to x86 instances, late 2020, we announced the M5 ZN, which has the highest clock speed compute instances. These are running at up to 4.5 gigahertz of sustained all-core turbo performance. As I said, these are optimized for compute-intensive applications, and that's the reason why we are selecting them or highlighting them for our verification topic here. These come in different instance sizes as well. So at the largest size, you can have up to 24 cores and up to 192 gigabytes of memory. And they have enhanced networking up to 100 gigabits per second of throughput. So another important piece that I wanted to touch a bit on regarding the storage side, and so typically for storage, we would have different storage services depending on the throughput and the IOPS and network performance that's needed out of the file system. So for ED workloads, we definitely recommend Amazon FSx for Lustre file system. It's a massively scalable. It offers a massively scalable performance that can reach millions of IOPS, hundreds plus of gigabits per second of throughput with consistent latencies. It's a parallel distributed file system. The resources that are deployed behind the scenes are all SSD based. There is an offering or a low-cost offering that uses HDD, but for high performance, we would recommend the SSD-based file system. And as I mentioned, this supports hundreds of thousands of cores, compute cores running in the cluster. And we had numerous success stories on using Amazon FSx for Lustre for EDA workloads. I touched upon earlier on the different EC2 purchase options. So going from left to right, we start with the on-demand compute price or on-demand option. And essentially, this is the most flexible pricing option that's available. You essentially pay for the compute capacity by the second without requiring any long-term commitments. And the on-demand instances are typically used for spiky workloads, or when you are not sure exactly what your needs are. So maybe you want to start experimenting and figuring out what your long-term needs, how they are going to be. And then after you have figured that out, maybe for your baseline of usage, you can start considering either using the type of instances that are in the second category, which is what we call the reserved instances or savings plans. So these are two different alternative methods that where you make a commitment either for a 1 year or a 3 year purchase, and in exchange for that, you would receive a significant discount off the compute price, because now we are essentially committing to use it for a certain term. Again, either a 1 year or a 3 year. And then finally, the spot instances. These are spare EC2 capacity, where we would offer them to customers at a savings of up to 90% of the on-demand price. So the spot instances are are commonly used for large scale and flexible workloads that can support this concept of termination and restarting. So in order to deploy a stack suitable for ED workloads on AWS, we are going to use a solution called Scale Out Computing on AWS. You can see the link at the bottom here. So this is actually the official framework that is used by Amazon Devices Lab 126 HPC environment. So this is the team that develops the Echo devices and the Kindle devices that some of you might be familiar with. And the main purpose is to enable engineers and scientists to be able to run EDA and CE workloads without actually having to have a deep knowledge on either AWS infrastructure stack or even Linux experience. So as I mentioned, this is an official AWS solution, which means that it is actually vetted for information security compliance, and it is used as a technical reference implementation designed to help you solve common problems and build faster on AWS. So the screenshot that you will see here would be a similar screenshot to the one that we will eventually log into when we want to start running the actual workloads for verification. So an important piece of the solution here is to have access to remote desktops. So the scale out solution that I mentioned in the previous slide uses another application from Amazon called NiceDCV, and that provides users with remote desktop. So think of it as like a typical remote desktop session. It has a native client that you can download either for Linux, Mac, or Windows, and it's also available as HTML5 for web clients. So it supports dynamic hardware compression, it encrypts the communication, and it also supports multiple monitors as well, besides using various peripherals that you might have on your laptop, for example, that's accessing the remote session. And NiceDCV is offered for no added cost when it is running on Amazon EC2 instances. So cloud use cases that I have discussed are probably more focused on the EDA or IP type collaboration chamber, but the reality is that the cloud enables multiple secure collaboration between different partners and vendors that you might be using. So you could use chamber for your own internal usage, and then maybe you want to give access to maybe like an IP provider, or maybe the EDA vendor, if there is something that you want them to investigate and look at. The IP provider could have their own secure chamber as well, that maybe feeds in data into your chamber. You could actually have other chambers for maybe yield analytics, or if you need to work on collaboration, for example, with the foundry, or and so on. So there are different collaboration chambers that you could set up in addition to the semiconductor secure chamber that you would be typically using to run your own workloads, by essentially providing access to some of the partners, uh, or in creating different chambers to provide access to some of the partners that you work with, again, to reduce the risk of exposure for example, to like a specific IP or a specific item that you want to share with them. But the idea behind running your workflows on AWS is to try to shift the process, or more of it, to the left side of the direction, so that you can actually do more analysis, more verification, and more yield and failure rates analysis early on, so that that can improve the likelihood and the success of your tape out. And again, that could include methods like analytics or machine learning that you can take advantage of when you are running some of these workflows in a cloud environment on AWS. So with that, I will hand it over to Melvin, so that he can talk about running Synopsys simulation workflow on AWS.
Thank you, Ahmed. Good morning, everyone. My name is Melvin Cardoso, and in this presentation, I'm actually going to go over what it takes to move simulation workflows to AWS. Most of this is based on our internal effort to move ECS regressions to AWS Graviton, and also what we've learned from multiple customers that we have collaborated with to do the same. So why would anyone want to move their simulation workflows over to the cloud? We've actually seen three types of use cases, all targeting higher QOR and faster TTR that is possible on the cloud. The first is your typical startup who has no existing IT infrastructure, and they're essentially looking to move all into the cloud because it provides them a managed infrastructure, obviating the need for their own IT team. The more general use case involves existing customers who have their own on-prem infrastructure who are looking to the cloud for two reasons. The first is for very short-term burst needs, when a project needs more cores for a simulation to meet scheduled deadlines. The other case involves more sustained peak access scenario, where they're looking for a large number of cores for anywhere from 2 to 6 months to meet tape-out coverage targets. This also covers the case where they are looking to expand long-term capacity using the cloud rather than add to their own data centers. Depending on the use case, the challenges that can arise differ. And in the next few slides, I will go over some of those challenges and how both Synopsys and AWS can address those challenges. The picture to the left of the dotted line is what a traditional EDA infrastructure looks like. And many of you may be familiar with most of the components in this picture. Starting bottom up, you have the data and storage layer. As many of you may be aware, in EDA, NFS is the predominant service that is used for this purpose, unlike the cloud, where an object store is a more widely used method of storage. Going up to the compute layer, most of EDA use bare metal machines, though some have been transitioning to virtual machines over the past few years. The cloud, on the other hand, started off with only virtual machines and containers. and all the compute machines on-prem are typically running the same OS version and tools. From a grid software perspective, the vast majority of EDA companies, with a few exceptions, rely on the commercial LSF or Univa grid engines. The cloud, on the other hand, offered either their own schedulers like AWS Batch or relied on the free ones like Slurm and PBS Pro. If you look at the workflows, each customer has their own homegrown workflow that's built according to their needs and has evolved over time. Being very custom to EDA and a company, there's not much in terms of cloud offerings in the space, which is not very surprising. Finally, looking at the user access layer, most of EDA uses either direct connection or VPN access to the compute hardware, though many will restrict direct access to the grid farm itself. And all access on the machine is typically controlled by standard Unix user accounts via a centralized LDAP architecture. We will cover the challenges at each of these layers next. So let's start with the storage layer. On the data and storage layer, the biggest challenge that we faced, and we actually heard the same from many of our customers, was how do we get the data onto the cloud and how do we continue to keep it in sync? As part of our internal effort, we tried two approaches to this problem. We started with the first one, which was a simple one that used lift and shift, where we identified all the required data using the Synopsys Cloud Transfer Packager, and then we continue to keep the data in sync using rsync. This does require you to run Synopsys Cloud Transfer Packager on-prem so that it can actually identify all the list of dependencies that can be packaged into a tar file. While this approach worked well, it does require constant maintenance to handle any new files that have to be synced over. The more convenient approach is to use a managed service. Examples like AWS Data Patch, Peer Cache, or Spillbox. In our internal effort, we use Spillbox to manage this for us. Most of these services work by automatically copying the data over when first accessed and caching them for further use. One other consideration for simulation jobs is that the I/O ops allocated for storage, like FSX Luster, has a significant impact on the performance. Allocating a larger volume will give you higher I/O ops, which translates to a faster simulation run. Of equal importance is the cost of the data transfer and storage. AWS has multiple offerings from storage with different price points, from EFS, which is very similar to NFS, to object storage. For our workloads, we ended up with a mix of EFS for storing important data that cannot be lost, to FSX Luster for the tools and test cases. We also actually made heavy use of NVMe local disk for running the jobs on to essentially reduce the load on the NFS. The data transfer costs were more manageable because most of our data was uploaded to the cloud, which has no transfer cost, though it took a significant amount of time to perform the first upload, which obviously depends on the amount of data you need to transfer. In our case, we actually ended up having to transfer a few terabytes of data over. Subsequent rsyncs were actually much faster because they just essentially rsync incremental changes. On the download side, which are charged, our fees were small because we only downloaded the summarized results of the runs. All failing tests were debugged on-prem, so we did not have any dump files being downloaded from the cloud. Simulations at scale tend to concentrate the file system load on just a few files in the data layer that can lead to poor NFS performance. These files are the simulation executable itself and the tool libraries that are read by pretty much every simulation job being run. Cloud-native architectures, on the other hand, are optimized for distributed file sharing at scale using non-POSIX compliant technologies like object stores. One VCS solution that tries to address both challenges of data consistency and scale are containers. VCS has the ability to compile a design into a Singularity or a Docker image, which contains most of the dependencies required to run the simulation on the cloud. This typically includes the SimV, the DIDER, and any required runtime libraries, including any user's PLI specified at compile time. It will, however, not include any test-specific inputs, so those would have to be copied over to the cloud separately, which is usually a one-time effort since those do not change too much. To customize the output, the user can specify their own base container image or pass in a file list of packages to be installed and a list of files to be copied into the image. Any external data can be accessed inside the container by mounting the appropriate volume inside the container. This is typically where any output from the simulation is stored for processing when the simulation completes. We also support a more generic container that has only the OS and VCS runtime libraries, allowing for the other data to be mounted into the container. This also helps to mitigate the stress on the storage, since all simulations that are running in parallel will be accessing those runtime libraries at the same time. Moving on to the compute side, one of the primary compute challenges in moving workloads to the public cloud is the cost differential. Using on-demand instances on AWS, which gives unfettered access to a machine when required, can be anywhere from 3 to 4 times more expensive than the on-prem cost for the same hardware. A lot of this actually depends to some extent on the machine utilization on-prem, but a 3 to 4x number is something that we've heard in general from many customers. To mitigate the cost differential with on-prem, companies can use spot instances on AWS, which are typically available at one-third the cost of on-demand instances. These instances can reduce the cost of compute, but they also present a challenge with the possibility of being terminated on a very short notice, potentially resulting in lost computations. Another challenge with spot instances is the availability of spot instances when needed for a burst. AWS Plot Fleet is an offering that can help mitigate the availability constraint. AWS EC2 also presents a problem of plenty, with the choice of instance types varying from half a gigabyte per core all the way up to nearly 16 gigabyte per core, and VMs starting from 1 core all the way up to 32 cores and even more. The cost, however, scales linearly based on the number of cores and the amount of memory per core. Selecting the right instance type for each simulation job can present a significant cost saving, especially for simulation jobs that are mostly single process. VCS technology makes it cost efficient to use these low-cost spot instances and also makes it easier to deploy simulation jobs on these types of instances. Depending on the size of the simulation job, VCS can be configured to do an immediate save of the simulation state when the instance is marked for termination. Execution Manager has the ability to automatically detect that an instance has been marked for termination and trigger the save when that happens. In addition, Execution Manager can be configured to automatically resubmit a job to the grid scheduler after the save has been completed, so that the terminated job can be restarted on a different instance from the same save state. For large jobs that cannot be saved in 2 minutes, VCS can trigger periodic saves with low impact that result in only a small amount of the simulation being lost. Our experience on AWS has shown that it takes about an average of 2 seconds per gigabyte of memory to perform the save. So the 2-minute warning on AWS is typically sufficient to save simulations using up to 50 gigabytes of memory, which to a large extent actually covers most simulation jobs out there. When it comes to the grid software, one of the considerations is how do you handle a hybrid environment? While setting up a separate grid server on AWS is quite straightforward, it does pose challenges in the use model for users because they would have to be aware of 2 different environments. In this regard, LSF Connect makes it simpler to address these concerns, where jobs simply need to be submitted to the local farm, and LSF Connect takes care of running the job on-prem or in the cloud, depending on compute availability. And most of the commercial and free schedulers do support the ability to dynamically bring up and take down instances when required, thus minimizing compute costs. One area that does require significant focus is the area of IP portability, because not all IPs allow usage on the cloud. Similarly, depending on the connectivity between on-prem and AWS, it might be more efficient to locate the license server on the cloud instead of using the on-prem one for cloud jobs. And many customers have been taking the approach of keeping the cloud environment transparent to their employees, so much so that in many cases, they are not even aware that the jobs actually ran on the cloud. While accessing this transparency does require significant effort at every layer in the infrastructure, it has been done in many cases. On the workflow management side for verification environments, Synopsys Execution Manager has been fine-tuned for AWS. This includes support for spot instances, as we talked about, managed databases, and data movement, to name a few. Execution Manager has also been extended to work with most of the schedulers available on AWS. And standing up an Execution Manager environment on AWS can actually be done very quickly using a few Terraform scripts. Finally, I'd like to end with a summary of our own internal efforts at running our verification jobs on AWS Graviton. As part of our support for VCS, VRD, and VIPs on Graviton, we migrated part of our regression environment over to AWS. This involved running about 250,000 plus tests on AWS. For storage, we relied on FSx Lustre for persistent storage, with the simulation jobs themselves using the local NVMe disks for scratch, which essentially actually helped performance. Data synchronization was achieved using both Synopsys Cloud Transfer Packager and Spillbox for managed synchronization, as we already talked about before. We use a UGE farm for this effort, comprised of the R6Gs or 16x large spot instances. Each instance was able to run about 2 jobs per core for a total of about 128 jobs per instance. And we scaled this up to about 2000 cores running in parallel, bringing down the regression time from 24 hours that it took us on-prem to about 2 hours on the cloud. With that, we'll now open up for Q&A.
So in this section of the workshop, I will show you how to deploy the scale-out computing on AWS solution. So what I did here is that I have logged into my AWS account. Then the first thing we are going to do is to go to services, EC2, in the region that we want to deploy the solution. So in this case, you can see I'm selecting the North Virginia region. You can deploy the solution in any region that has at least 3 availability zones. So what I'm going to do is go and create a new key pair, because the solution would need one. So I already have a key pair, but I wanted to show you the steps in case you don't have one already. So you click on create key pair, and then you will give it a name. So let's call it DVCon. And then you choose the file format, depending on if you are on a Mac or Linux, you would typically use the PIM key. If you are on Windows, you would use the PPK key, and then you will need to convert that with Spotty into a PIM so that you can SSH to the scheduler node that the solution will create here. So you give the key pair a name, you click on create a key pair, that will create a pair, and then the browser will prompt you to download that PIM key. So you will go ahead and save that key because we will need it later on. And then in the next window here, I have opened the aws.amazon.com page. So I'm going to click on Solutions and then AWS Solutions. And then in the middle of the screen here, I'm going to click on AWS Solutions Implementations. And then in the search, I'm going to search for scale out. And then hit enter. So this will open the page for the solution. So we don't need this one anymore. So this is like a simplified architectural diagram of the solution. So what it does is that it's going to deploy at the heart of it. Obviously, it's going to create a virtual network and subnets. It's going to create in the public subnet a scheduler node. This will be the primary node of the cluster that's going to be running OpenPBS, and we will be able to SSH to that node and start submitting our jobs. Another way, we will also create an elastic load balancer and our DCV sessions. So on the scheduler node, we are also going to be running a web server. So the elastic load balancer, when we hit the URL, it will redirect to the web page of the that's running, or the web server that's running on the scheduler node. We log into that with the username and a password they're going to create when we are deploying the solution. And there we can create what we call DCV graphical sessions so that we can access a desktop node and be able to see like a full desktop on that node. The automation for the scale out computing uses EC2 auto scaling so that it can create new EC2 instances when we submit jobs into the cluster. These instances would mount two file systems that are created by the solution using Amazon Elastic File System. It can also mount Amazon FSx for Lustre file system, and we'll show you the steps that are needed. Again, for ED workloads, we typically recommend that the workload would be running on Amazon FSx. Also, the solution deploys an Elasticsearch service that's used to capture some analytics information about the jobs that we are submitting, the users, and so on. We'll probably not have enough time to cover these features in our session today. But I'll go ahead and click launch in the AWS console, so that will open the service we call CloudFormation with a link for the template to deploy the scale-out computing in AWS solution. So I'm going to hit next. Again, before you move on to the next page, again, ensure that you are in the right region. So I'm going to hit next here. The stack, we will give it a name. So let's call it DVCon. And then you scroll down, you will see that the S3 bucket should be filled already, and similarly the folder that has the solution should be filled already. So I'll skip that. Then the Linux distribution, you can choose which distribution you want to use, or which OS you want to use for the different nodes in the cluster. So the cluster allows to have on the compute nodes can be CentOS 7 or L7 or Amazon Linux 2. So I'm going to keep it as Amazon Linux 2 because I want to use that for my scheduler. And then we can modify and create our custom compute node to use CentOS, for example. And there is a link here that if you want to use CentOS 7, that you will need to subscribe to that CentOS image on the marketplace so that you can use it in the solution. Next, we'll go to the instance type for the scheduler host. I'll leave that as the default M5.xlarge. That's typically sufficient for maybe 1,000 jobs or 2,000 jobs concurrently. If you think that your cluster might be running more than that, maybe you want to increase the size like M5.2xlarge or 4xlarge. But for now, I'll leave it as M5.xlarge. Next is the network. So the VPC, or the virtual private cloud that the solution will create, it needs to allocate a network range for it. So I'm going to use maybe 10.1.0.0/16. And then next, it's asking for my IP. So this will be the public IP of the host that I want to be able to use so that I can SSH and open port 443 from, so that I can log into the web server that's going to be running on the scheduler node. So I'm going to open This link here points to ifconfig. It's a website to detect my public IP. So I'm going to copy that and put it here. And then it asks for the SSH key pair. So I'm going to select the key pair that I've used earlier, and then a username that I'm going to use for as the default user for default LDAP user. That's also going to be running on the scheduler node, and then we can use this user to add more users if needed. And then it asks for a password, so I'm going to type a password here. Okay, and then we hit next. We go on to configure stack options. We not really need to do any changes, so I'm going to hit next on this one. And then we will review the items that we have entered. And I'm going to scroll all the way to the bottom and then acknowledge that the solution can create IAM resources, which it does, and start the process to create the stack. So I will leave. So the stack is going to now going to deploy. There are 7 substacks that it is going to deploy. So I'm going to pause the video here and come back when all the 7 stacks of the solution have deployed. So as you can see here on the screen, the stack progress is still ongoing. I wanted to wait until at least the network and the security stacks are completed, so that we can start doing some of the other things that we need to create while the rest of the stack is being deployed. So in the network stack, you can actually click on events and you can see exactly what is it doing, or you can click on resources. So you can see it created, if you scroll down, you can see it created a VPC, internet gateway. It created the subnets, created 3 public subnets and 3 private subnets. It created route tables and the associations with the route tables, and internet gateway and elastic IP that we're going to use for our scheduler node so that we can always access it with a specific IP address. And similarly, the security stack completed the IAM roles and the security groups that are needed for the scheduler to be able to scale out or scale up and scale down the cluster, and also the security groups to make sure that the nodes within the cluster can communicate with each other. And you can actually see the details of the implementation of the scale out solutions. It is documented on the page here, but you can actually see the source code on GitHub. The solution implementation is actually open source. So now that the network and the security stacks are deployed, I'm going to create 2 additional things that we are going to need for our EDA workload. The first thing is a server to act as a license server. So I'm going to create an EC2 instance for that, and I will walk you through the steps of the parameters that you will need to provide to your EDA partner, in this case Synopsys, so that they can generate the licenses for you. So let's go ahead and get started with that. So I'm going to close this page since I don't really need it anymore. I'm going to click on Services, EC2, and then on Instances, I'm going to create, so this is the scheduler node that's being created. You can see it's still initializing. I'll create another node in the network here so that I can use it, as I said, for the license server. So I'm going to search for CentOS. I'll select CentOS 7. And I will click continue. You can see the the CentOS 7 software is free. You only pay for the cost of the compute instance or the server that it's going to be running on. So I'm going to click continue on that. And then typically, again, depending on the scale, you would want to select a certain instance size in terms of memory and a number of cores to support the activity. So for this example, I'm going to use a C5.2x large. It has 8 virtual CPUs, meaning it has 4 physical cores with hyper-threading on. So it's 8 virtual CPUs and 16 gigabytes of memory. So I'm going to select that. I will want to deploy that in the VPC that was created by the solution. I will deploy that in the private subnet. And I will leave the rest. 8 gigabytes on terms of the storage is okay. If you want to increase that for any reason, you can. Usually, there is not much you install on the license server other than for example, the Synopsys Common Licensing application, and that usually doesn't require significant space. So I'm going to leave 8 gig, and then you go on to the next page where you type the tags. I'm going to create a name tag and just call that license server for now. And then click next on configure security groups. I'm going to select an existing security group and then select the compute node security group that was created by the SOCA solution. Again, you can see the name here, and it starts with DVCon, which is the name of the stack that we deployed. I'm going to click View on Launch and select the key pair that we want to use for this. Again, in case we need to SSH to the node, and then we will. So I will select this and then launch the instance. Okay, so while the instance now is being launched, so there are 2 key things that you need to be aware of on terms of licensing for ED workloads. So for Synopsys Common Licensing, there are two methods on what would be the host ID that you are going to use for the license. And again, you can see the details once you download the latest version of Synopsys Common License SCL, and you install that. And then in the documentation, it will walk you through like some of the CentOS 7 package dependencies that you need to have on the host. And then you install the application and run the commands. And then you have 2 options in terms of figuring out what will be the host ID that you want to use. The first one is what we at AWS call the instance ID. So you can copy that, and then essentially in the Synopsys Common Licensing, they call it the virtual machine universally unique ID. So essentially the string that you will provide to Synopsys will be something like VM_UU ID equals, and then the host ID. So that would be the first method, and essentially you will send this number to or this string to Synopsys so that they generate the license key versus this one. So the benefit of this method is that it is now the licenses are going to be tied to this instance. So again, this is a virtual machine. So if anything happens to it, you can simply stop it and restart it, and it will run on a different physical server, and things will continue to work. But in this instance, for example, is specifically running on a specific availability zone. So if you want to start another license server in a different availability zone, for example, then the new server will have a different instance ID. So in that case, you will not be able to use that same license file that Synopsys provided to you for the new license server. So another method that that Synopsys allow is that you can attach what we call an elastic IP and attach that to your license server. The benefit of that elastic IP is that you can actually detach it from one server and attach it to another one. So let's go ahead and see an example of that. So we will go ahead on the network and security under elastic IPs. Then we will allocate an elastic IP. And so in this case, we are running in US East 1. So I will leave this as is. Maybe add a name tag for it. And then let's call that EIP for license server. And then say allocate. And then we go ahead and click Actions and say Associate Elastic IP address. And now in the instances, we search for our license server and attach it to it. And then on reassociation, you can say that we want to allow this elastic IP to be reassociated. So basically, that would allow us to move it to a different instance, for example. So now we hit associate. So now it's associating this this IP address with our license server, and now the string that you will provide to Synopsys to generate the licenses will be something like Amazon underscore EIP equals and then the IP address. So this will be also a unique string that's now unique to this license server, but you can, if anything happens to that license server and you want to start another one, you can now go here, select this elastic IP, disassociate it from the first server, and now go ahead and create another server, and then come back and associate this same elastic IP to the new license server. And then this way you can use exactly the same string here, which is basically associated with your license file or entitlement file that Synopsys will provide, so that you can essentially reuse the licenses that Synopsys provided on the second one. Again, the elastic IP cannot be associated to two license servers, for example, right? It's only associated or with one license server at a time. So these are the tips that I wanted to share regarding creating an instance or an EC2 instance to act as a license server for our workload. I will skip the part where we download like Synopsys SCL and install it. Again, I would recommend that you download the latest version, and the documentation has all the details and necessary steps to identify again which one of these two methods we are going to use for the host ID and the steps to setting it up. So the next step is to create a file system. But before we do this, I'm going to go to our object storage solution S3, and I am going to create a bucket to be associated with what we want to work on here. So I'm going to click on create bucket and give it a name. The name needs to be globally unique. So I'm probably going to add my username here and see if that is globally unique enough or not. And then I will leave all the defaults for now and go ahead and create bucket. So good, the S3 bucket is now created. And again, you can see that I kept the option to not make it public because that's exactly what we want to do. So this is the bucket that if we are going to bring in any data from like, for example, the test cases that we want to run or the software version that we want to download and install, you want to put these large tar files into S3. So we can easily upload them from here, or again, your admin can upload them if they have an access key using the AWS CLI to upload the data into the S3 bucket. And now we are going to create an FSX file system that's attached to this S3 bucket. The benefit of that is that this integration between the two, we will immediately see the data that's in that we have created or uploaded to our S3 bucket in the Amazon FSX for raster file system that's attached to this bucket. So the metadata of the objects that we are creating, exactly, simply the file names, the owners and file sizes and all that will be loaded when the file system is created. But then the actual content of that data will be what we call lazy loaded. So it will be loaded on demand when you try to open the file. Then on the back end, it will download the content from S3 onto the servers that are used by the Amazon FSX for raster file system. So is that now I have the bucket in place. I'm going to copy the name so that I can use it in the next step. And then I'm going to go to Amazon FSX and click on create a new file system, and then select Amazon FSX for raster, and then click next. Here I'm going to give the file system a name. So as you can notice that there are options for the deployment of the file system. There are options for the throughput for the file system per unit of storage and the storage capacity. So these are the parameters that we will typically specify to create the file system. And then the service will take the overhead of like deploying the file system, configuring it, and just giving us the endpoint for how to mount the file system. So the options that we can choose between are either to use persistent SSD, persistent HDD, or Scratch SSD. Typically for ED workloads, we recommend that you'd use an SSD alternative. The main difference between the persistent and the Scratch is that the persistent file systems replicate the data within the availability zone. So if you are going to create like new original data in the file system, then the recommendation is to use persistent SSD tier. But if you are going to use it, maybe as the name implies, for Scratch, the data is not original. You have a copy of it already in prem, or maybe a copy already in S3, and we'll just use the file system just for the sake of where we run the simulations and dump all the intermediate files that it creates, then maybe we can use a Scratch file system. So for our use case here, we probably can go ahead with a Scratch file system. And when you select the Scratch file system, you'll notice that the throughput tier is automatically selected to the 200 megabytes per second per terabyte. While on the persistent tiers, you can actually get to choose. So if you will go with a persistent SSD, then you can choose between 50 megabytes per second per terabyte, or 100 megabytes per second per terabyte, or 200 megabytes per second per terabyte. Note that these numbers are normalized to the storage capacity. So again, depending on the file system, you can, or the file system type, you can have different sizes. For persistent SSD, again, we can start with 1.2, an increment of 2.4. So you can see here, because I'm selecting the throughput to be 50 megabytes per second per terabyte, and I've selected 1.2 terabyte for the storage capacity, the throughput capacity is now calculated as 60 megabytes per second. If I switch this to the 100 megabytes per second, then you can see that throughput capacity has increased. Similarly, for 200, it increases as well. Another important factor to consider here is IOPS. Again, the number of IOPS that the file system can create is also directly attached or related to the storage capacity. So for AD workloads, maybe you want to start with a 2.4 or a 4.8 file system. And if you notice that the performance is not sufficient, or you need more IOPS while you are monitoring the file system, you can increase the storage capacity later on. So again, if you need like tens of thousands or hundreds of thousands of IOPS, then the recommendation would be to go to like a bigger file system, maybe a 48 terabyte file system or an 84 terabyte file system or something like that. For now, I'm going to go with persistent file system, 200 megabytes per second per terabyte, and we'll go with the 4.8 terabyte storage capacity. Next, I'm going to select the VPC where I want the file system to be deployed in. I'm going to remove the default security group and add the two other security groups that were created by the Soka stack, the scheduler security group and the compute node securities group, so that we can mount the file system on the scheduler node and all the compute nodes. These two security groups have the required ports to enable that. And we'll select the subnet. I will select the subnet to be the first private subnet, so I'll leave it at that. And then we can select the encryption key. I'll go with the default encryption key. And then now when it comes to the data repository import and export, this is where I'm going to use the S3 bucket that I had created earlier. So I'm going to select the option to update my files and directories listing as objects are added to or changed in my S3 bucket. So when we add newer objects into the S3 bucket that we created, we can easily see them in our file system. So now I'm going to add the name of the bucket that we have copied earlier. And then for the import prefix, I'll leave that empty because we want to import everything from the bucket. If you had like subdirectories in the bucket, you can add these, or what we call a prefix, so that you can maybe limit the file system to only see that prefix or that directory only. And then for export, I'm going to use the option to use the same prefix that I'm importing from. So if I'm importing everything, I should be able to write anywhere so that I can update the S3 bucket if I need to write back any data at the end. So now next, I'm going to click on next, review all the parameters that I've specified here. Everything looks okay. So I'm going to go and click on create file system. So this will start the process to create the file system. This process typically takes 5 to 10 minutes, again, depending on the file system size and depending on the if the S3 bucket that we have linked the file system to has too many files that it needs to index. So I'm going to pause the video now, and I will resume when the file system is created. Okay, so now our file system is ready and available. So I will click on the file system ID, and then I will copy the DNS name, because I'm going to need that so that I can update a configuration file on the scheduler node so that it can mount this file system. So I will leave this window open. I'll go to the other tab where I had my list of instances. I'll select the scheduler, and then I'll click on connect. You can actually, if you have the SSH key that we created earlier, you can use that to SSH from your machine that you are using or your laptop to the scheduler. I find it easier to just use the instance connect in this case, because our scheduler is running in a public subnet, and it has the session manager application running. So that's how we can easily connect into it. And again, the AWS Systems Manager session manager was installed by the Soka scripts. So I'm going to become root on this. Then you could do the f-h. You can see that there are two file systems that are mounted, one on /apps and one on /data. These are two file systems that were created by the scale-out computing solution that use the Amazon EFS service. So /apps is where the solution installs all the automation scripts to scale up and scale down the cluster and the web server that's running on this node. And /data is used for the user home directories that will be created. So I'm going to create a new directory for /fsx, and then before I mount it here, I will modify the path or in one of the configuration files so that the DNS name that we copied can be used, so that we mount the node, mount the FSX file system on all the compute nodes that will be created. So I'm going to go to cd/apps and then soca, and then soca dash the name of the stack, and then I'll go under cluster manager settings. And then if you do ls here, there is a file I want to edit, which is qmapping.yaml. So in the first section under compute type, I'm going to add a new entry here and say fsx_luster. And then between double quotes, I'm going to paste the DNS name of the file system. While we are on this screen, there is also another thing that we will want to modify. So in this case, because I deployed, if you remember when I deployed the stack for the scale-out solution, I selected Amazon Linux 2 as the base OS. But and this is and you can check that if we close this file and do cat/etc os release, you can see that the OS version that's running on the scheduler node is Amazon Linux 2. For ED workloads, I want to use CentOS on my compute nodes. So I'm going to go to services EC2. I just need to know the image ID or the AMI ID for CentOS 7 that I can use. So I'm going to click on sorry, I'll click back on launch instances. I'll click on the marketplace. I want to search for CentOS. Can click on more info, and then click on this page. This will open the marketplace page for CentOS 7. I'll click on continue to subscribe. And so this is CentOS 7 for x86, and in North Virginia, this will be the image ID that I will need to copy. If we want to find the image ID for Graviton2, it's there are a few more clicks that we'll need to do. So we'll go back on the product detail, and then we'll open this CentOS page on a new tab, and then from here click on visit CentOS.org website. That will take us to a wiki page on the CentOS website for AWS that has a list of the image IDs for the different versions of the operating systems they have published in the marketplace. So if we scroll down on this page, we can see CentOS 7 for x86 for the various regions, but then again you can see CentOS 7 for ARM, the ARM architecture, again for the various regions. So for R64 and US East 1, so this would be the AMI ID that we will need to copy. So I'm going to copy that. And then now we'll go back onto the onto our configuration file. We will edit this instance AMI, and we put in the AMI ID that we just copied. So since we want to run on the Graviton2s, we will need to have the default instance type, something that is C6G, for example, .large. And then we will need to add base_OS CentOS 7. So this tells the scaling scripts that we are going to create that this AMI that we are using here uses a different operating system as the one that we are using for our scheduler node. Okay, so now that we have edited this file, we will go back to our CloudFormation stack and check the status. At this point, all the 7 layers should be in create complete, as you can see here. So again, the network and security were done before we started creating the license server and the file system. Then it went ahead, created the storage, where it created the 2 EFS file systems, created the scheduler node, and the analytics, the load balancer, and the some additional configuration that SOCA needs. So now we are going to click on the main stack that we created, and we click on outputs. So we'll see here there are 2 links. This is going to be the main link that we are going to use to access the web server for SOCA cluster. So I'm going to open this in a new tab. Okay, so we see that now the web server is loaded, but because we're using HTTPS and we created a self-signed certificate, the browser is giving us this warning that there is a potential security threat. So we'll click on advanced and accept this, and then the page will reload, and now we are on the login page for our cluster. So I'm going to type the password that I created, the username and the password that I created when I was deploying the stack, and I will log in. So at this point, our cluster is ready. So I'm going to turn it over for Melvin to take us through the steps for submitting and running the VCS simulation jobs.
Ahmed. So what I'm going to do in the next session is actually to try to use the SOCA environment to upload an Open Titan design and then run that on a Graviton processor using VCS 2020.12. So what we'll do first is go ahead and create a desktop. Let's go ahead and create a Linux desktop. I'm going to call it Graviton Linux. I'm going to pick the stack. I'm going to use the R6 instance, R6G instance, which is actually a Graviton machine. Let's go ahead and launch the session. Okay, so this takes a little bit of time to come up. So while that's coming up, what I'm actually going to do is to take the design that I have on my laptop and then move that over to the SOCA environment. There are multiple ways to do that. You could use SFTP. What I'm actually going to do is the more simpler SOCA file explorer. So let's first go ahead and create the tarball. So this is my design, and I'm going to create a tarball. Okay, now that I have that, let's go ahead and upload it using the SOCA file explorer. I'm going to put that in my public folder. Let's go to upload files and drag and drop. Okay, so that should take a few seconds. And there we go. So that's the Open Titan. Okay, so now we have to wait for the desktop to come up. While the desktop's coming up, I'll show you there are actually multiple ways to log into the desktop. You could use SSH to log in, but what we are actually going to do is once it comes up, there will be an option here to actually use the browser to actually log in, and that uses the nice DCV component of SOCA. So let's give it a minute while the desktop comes up. Okay, so as you can see, we now have our desktop running, and this is what I'm going to use to actually launch a browser session to connect to the desktop. And that actually launches a nice DCV, which now gives us essentially a terminal. So let's go ahead and launch a terminal. And if I look in the public directory, I now have my Open Titan design that we had uploaded earlier. As we talked earlier in the session, what I'm actually going to do in order to run the design is actually copy the design over to an FSX Lustre volume. That Lustre volume has already been created and mounted, and you should see that under, where am I looking at? Right there. So it's been mounted under /fsx. So let's go to /fsx. I already have a subdirectory in there. Okay, so let's go ahead and create a directory and untar what we just copied over. Okay, so we now have our design here. So what we have to do next is to compile the design, and so I already have a script to do that. And that's my script, right? So as I said, we're going to use VSys 2020.12. I'm actually going to compile this locally on the volume and not actually submit it to the grid. And so let's go ahead and source our settings file first. And that's just going to set up the path to the license server. And now we should be able to start the compile. The compile script. It's a relatively small design, so it shouldn't take too long to compile. Okay, and the compile is done. So in order to run the design, I already have a script. And in this case, we are actually going to submit the jobs to the grid. We have a queue called always on, and the script actually takes a parameter that tells it how many jobs or how many SIMVs do we want to run in parallel. So what I'm going to do right now is I'm going to run, let's say we're going to run about 8 jobs in parallel. Okay, so we've submitted our jobs. Now let's go ahead and look at the queue at this point. And if I click on that, you'll essentially see that we have our jobs running. So the jobs take about somewhere between 10 to 15 minutes to run. So what I'm actually going to do while we wait for that to finish is I'm going to go over a little experiment that we did as part of moving VCS regressions to Graviton. So what we did is we took the same OpenTitan design and we ran it on an R6 G16X large machine. The OpenTitan design takes about a little less than 1 gigabyte of RAM. And if you look at the Graviton instance we are using here, it has 64 cores and about 512 gigabyte of RAM, which translates to about 8 gigabyte per core. For storage, we actually use FSX Luster. This is the results that we found when we actually ran jobs in parallel. So the first column identifies the number of jobs that were run in parallel, and the last column actually identifies the amount of time it took on an average for each job to run. Remember that this has 64 cores. So in order to do this, I'm going to go to a chart to make it a little bit easier to understand. So as you can see, the amount of time that the jobs took to run jobs, and these are the number of jobs running in parallel, it stayed pretty much very close to the amount of time it took for a single job. So I think the single job took us about 1100 seconds. And as you can see, even when we were running 160 jobs in parallel, we ended up taking only about 1186 seconds on average for the jobs. Now, of course, one caveat is this this is obviously going to be not design specific as much as probably the amount of memory it takes, because in our case we were not memory limited because we had about 4 gigabytes per core, whereas 8 gigabytes per core, whereas the OpenTitan design takes only about 1 gigabyte per core. So even if you end up with a design that's taking close to about 8 gigabytes per core, we expect that the performance actually would be something very similar, right? Where even if you end up running 2 jobs per core, the performance actually does not degrade too much. And this is something that we actually used when we were figuring out how many slots we set up on the grid farm for each of the R6G instances we were running for running our regressions. Our regressions also take less than about 4 gigabyte per core for each process. And so we ended up about 2 slots on each process, right? And that allowed us to actually get, the same amount of throughput at a much lower cost, right? Essentially half the cost of what we would normally have paid. Okay, so let's go back, and as I said, this is going to take a little bit of time for the designs to complete. Okay, so while we wait for the jobs to finish, what we'll do is let's try to go and look at what I can do from the job queue. So in previous, so obviously I could submit or I can kill jobs from the command line, but there is a possibility for me to also do that from here. So if I want to kill this particular job, let's go ahead and try to kill that job. There we go, that job's done, right? Now let's look at see what job info shows us. And so job info will, for example, show us the directory. It's going to show us the execution host and a little bit more information about the job, including the environment and so on, right? It's very nice. And I can also actually look at the job directory from here, which will essentially just open up the file explorer. And now I can see, pretty much what I can see from the terminal, right? And as you can see, some of these files have already started to get created. So let's go back to a job queue. And now we only have 7 jobs because we killed one of them. So if I do a queue stat, right, so that's the same as what we were seeing in the job queue. And if I look at the log files are starting to get created, right? So let's look at one of them, and the design's running, right? So as I said, it takes about 10 minutes for the jobs to finish, actually closer to 15 minutes for the jobs to finish. Okay, so let's go and see if our jobs have now finished. And if I go to my job queue, the jobs are all done. Let's go back here and look at all our jobs, and queue stat should show me no jobs as well. And as you can see, let's take a look at run.8.log and the test passed, right? And if you see we had killed one of the jobs, that's going to be the run.3.log, right? That's all I had, and we'll go to Q&A from now. Thank you.